Okie dokie. So, in terms of tests, you can help yourself by doing the homework well today and tomorrow to prepare for the test. Every homework is a practice test in a way. So here we go. The notes. Did I put out the notes? Are you ready to go with the fundamental theorem of calculus? Oh boy, it's really pretty great. I think you'll love it. Okay. So, sorry, I got an extra period in there. You're leaving the student lot, all right? Your velocity over 6 seconds is t squared minus 2t feet per second. And you want to figure out how you're going to travel, how far you're going to travel. More like how, I should say how you will travel, not how far, in the first 6 seconds. I'm going to cross out far. All right. Would you sketch the velocity graph on your own real quick, please? Let me turn this over here. Oh, wow. How are we doing? All right, so what do you know? What's the shape? What do you know about the graph? Parabola is 0 is at? 0, 2, opening up or down? All right, so something like this, yeah? Not drawn very well. Hi. Thanks. Okie dokie. What are you moving forward and what are you moving backward? What are you backing up? Backing up on?
0 to 2.
On 0 to 2, not inclusive because? Because?
You don't come to a complete stop.
Because velocity is negative. Okay. When are you moving forward? Forward on 2 to 6 because velocity is positive. All right. Cool. Now, in terms of preparing for ye old test Thursday, you should now be able to do some basic infinite Riemann sums to find area under a curve. Will you give me the area you travel backward, which is to say this area? The area under a curve from 0 to 2. Feel free to work together. That is a infinite rectangle problem, so you should hopefully be able to do that. The first one's easier because it starts at time 0. the two to work together and talk to them.
And I don't first and close to
Oh, wait, the second one first. So, like the I squared.
I mean, I did the entire problem. It's 2 over n, it's 1 n over 2. Okay, how's it going? Okay. I know exactly
I'm
what
still not getting the right answer. Well, even if it's supposed to be here,
Okay, let's see how you did. Did you start off with, did you use delta x and f, or did you say delta t and v? I hope you used delta t and v, because that's what this problem's about. Yes? Delta x is not a problem. There is no x. So, start, if you already made that early, did you write over your delta x's with delta t, and your delta f's with v? Okay, next thing. Did you get that delta t is 2 over n? Okay. Next thing after that is, did you set up the calculation of the function is the function squared minus 2 times whatever?
Yes.
And in those whatevers put 2i over n. All right, now the next step is, depending on how fast you are, extracting the n stuff and leaving the I stuff. So here, when you distribute and take out all you can, what can you take out front of the summation? 4 or 8? 8 over n squared or cubed? 8 over n cubed times the sum of a bunch of I squareds. And what about when you go here? When I go this, it's 4 over n, 8 over n, so minus 8 over n what? Squared or cubed? There's one in there, one in there, so that's squared, 8 over n squared, and a bunch of i's. How'd that go? Analyze where your mistake was if you made one. Okay? All right. Now what do we do? Not yet. 8 over n cubed times, what is the sum of a bunch of squares? N times n plus 1 times all over 6. Minus 8 over n squared times the sum of a bunch of i's is? All right, cool. All right, so far so good. Now, what do we do? Limits, yes. Obviously, the only way that anything happens after that is if you take an infinite limit on that. I can't tell you how many homeworks I graded where people just had this and then all of a sudden they had an answer. Well, with no limit, there is no, it doesn't go to anything, you don't get an answer, you're crazy, it's just a formula, all right? If there's no limit, you have no clue. Or sorry, if there's not a limit, you have no clue, sorry, is what I meant to say, okay? You are taking the infinite limit to that. So, what about the top here? 8 times 2 over 6 is? Let's go with 16 over 6. Minus 4, okay? That's maybe 8 over 3 minus 12 over 3. I don't know if that's cooking you out, but that is negative 4/3. Now, if that bothers you, it's okay. I know negative area is kooky, but it's happening because a lot of values are negative, and that's okay. Okay? In fact, it's to be expected. It was moving backwards. So that if that is how far you moved, that's how far you moved backward, then it's negative is 100% correct. It's right on. You with me so far? Did you have anywhere close to enough room to do that one? No. Oh, well, you're in deep trouble now because this is going to be way more work. Sorry, my bad. This is about to get ugly. So, we might have to borrow a little area from some other space. We'll figure it out. But so here we go. How would you say? How about how far forward? We're going to talk the rectangles from 2 to 6. Okay, so it's the same idea. The area function is delta t times v at t sub I. Delta t now is 4 over n, and v at, now v at what t's is starting now at 2. Remember when the t at which it goes is the starting value of the region plus how many deltas over. So it's 2 plus 4i over n. Okay, that represents the x's at which you're drawing your right rectangles. Starting at 2, you go 1 delta, or 4 over n over, and then 2 4 over n's over. So this represents starting at 2 and going over, so many 4 over n's, and then drawing the height, right? Here's where we start to get ugly. The function is blank squared, leave a parentheses and big parentheses because we're going to put that whole sum in, minus 2 blank. And what x or t are we putting in each time? In this case, we're putting in 2 plus 4i over n each time. You follow? Okay, here's where we need to stretch this out a little bit. We're going to need to expand this. So leave the 4 over n out, and in the brackets, what do I get when I expand 2 plus 4i over n all squared? You want me to write it here so you can look at it? Here is 2 plus 4. Okay, so first is 4. Then, bless you. Good one. The OI is 8i over n and 8i over n. So the OI is 16i over n. And the last is 4i over n times 4i over n. 16 I squared over n squared. You with me? Okay, we got this done. Now we need to distribute negative 2 to 2. Negative 2 plus 2 is negative 4, and negative 2 times 4i over n. Talk to me, people. Negative 8i over n. Let's combine like terms. 4 over n is fine. Inside the brackets, what's the total of the constants? 0. What's the total of the i's? 8i over n. And what's the total of the I squareds? Okay, now we're getting to the point where we can break it into summations. So, one summation of the i's, what goes out front? 32 over n squared times the sum of a bunch of i's. And when we get to the n squared, I squared-ish stuff, what goes out front? 64 over n cubed times the sum of a bunch of I squares. Cool. Now we're getting somewhere. What do we replace i's by? N times n plus 1 over 2. What do we replace the I squareds by? N times n plus 1 times 2n plus 1 all over 6. Shall I pause for a second? Are you catching up or are you good? Okay, now we have this big old formula for a rectangle estimate based on any number of rectangles. Now to get the perfect area, I want to let the number of rectangles go without bound, or go to infinity. If I take the end behavior on the first limit, what do I get? 16, or 32 over 2. On the next one, what do I get? 64 times 2 over 6, I heard a little bit of, yeah? So isn't that something like 64 over 3? Okay, what's the common denominator? 3, so 48 over 3 plus 64 over 3 is 112 over 3. Does that simplify, or am I dunners? Dunners, okay. What does 112 over 3 represent? Area, and we just found how far it goes? Forward. Okay, forward. Cool. Now, if you're thinking, oh, that's hideous, there's got to be a better way, well, here we go. Actually, I've never answered the question I posed because I took this space. What does the sum of the two areas is, what did I say the first area was? Negative 4/3, and the second area is 112/3. So isn't that 108/3? And 108/3 is that not clean? That's clean, right? 36, yeah? Okay, what does that represent? That's the total of backwards 4/3 and forwards 112/3. That's the displacement. It's the difference between how far you went back and how far you went forward. So this implies that you are at time equals 6 seconds. I am 36 feet forward from where I started. Yeah? You follow me? All right then. Now, for thousands of years, that's the best you could do. Is you can say there was no limits, I guess. So you just do a bunch of rectangles and say, yeah, you're about this far. That was the best you could do because there was no calculus. But then, in the invention of the calculus, it wasn't too much longer that somebody said, now wait a second here. Newton's idea of derivatives can be applied here maybe. Let's talk about this. So, I wanted change, we just found change in position or displacement, yeah? I totaled out forward movement, backward movement to get change in position or displacement. Now let's look at this a little different way. I had velocity and I wanted to talk position. Well, what's the velocity-position relationship in calculus? Velocity is the derivative of position. Okay? Now, we could take that differently and say, okay, velocity is the derivative of position. I could also say that if I took the antiderivative of both sides, then doesn't that imply the antiderivative of velocity is, what's the antiderivative of the derivative? original function. So besides saying, all right, velocity is the derivative of position, I could also say position is the antiderivative of velocity, right? You agree? Okay. So if I had the velocity function to start with, I could actually get the position function by undoing the derivative, which we do by integrating. Now, that would mean the position function could be found by saying, all right, forget this velocity stuff. I'm going to anti-differentiate velocity, which was t squared minus 2t, to get what the position function had to be. What is the antiderivative of t squared? 1/3 t cubed. And what's the antiderivative of negative 2t? Negative t squared. And then we usually get a constant integration, right? You with me? So that plus c, I don't really have an initial condition going, so I'm just going to leave it there. You with me? All right. Now, once I had the position function, I could find change in position. We said the whole problem is about how did the position change? From 0 to 6 seconds, how did the position change? And we did all that infinite rectangle stuff in order to find that. But couldn't we just say, all right, if I want the position changed, doesn't that mean I just want to say, what's the position at time 6? What's the position at time 0? And change is the difference between the two. Now the position at time 6, that would be something like 1/3 6 cubed minus 6 squared plus some c that would relate to where we started from. You follow? And position at time 0 would be 1/3 0 cubed minus 0 squared plus c. Make sure you have parentheses around both because you need to subtract the whole thing. Now, the c's subtract away. I think you'll agree. Yeah? So what about 1/3 6 cubed? What do we get there? $36. 6 cubed is 2. What's 6 cubed? 36 times 6. So that's 30 times 6, which is 180, plus 6 times 6, which is 36, 216. Okay, so this is 216 over 3 minus 36. What's 216 over 3? 72 minus 36 is 36. Now, isn't that exactly what we got from the infinite area stuff? Yeah? So it seems like we found a bit of a shortcut that can help us avoid all this infinite rectangle stuff. It seems like if I want to find area under velocity, I could just say, well, shoot, I just need to take the position function by getting the antiderivative and then taking the difference. Not today, please. That would be super. Okay? So, it seems like another way to find area under curve is to take the antiderivative, then subtract. I mean, that's what we did. We got p by finding the antiderivative, and then we subtracted. P at 6, the endpoint, minus p at 0, the starting point. Now, the notation for that would look something like this. We took the antiderivative of velocity, and that's an indefinite integral. But because we wanted to talk about over a definite time frame, instead of an indefinite integral, we actually used endpoints. And that's what makes it a definite integral. You could think of this as representing the area under the V curve from t equals 0 to t equal 6. We could do all that summation notation, and all that's great, but really what this is standing for, this S stands for the sum. And so it is really the limit of sigma, the limit of all the sums. So that definite interval, that S, they didn't use that S for no reason. That stands for infinite sum of many rate times time calculation, yeah? Now we just said that that's equal to the antiderivative, which is position, and subtract. So when we took the antiderivative of velocity from 0 to 6, we added all those rate times time calculations, or summed them. It's equal to just the difference between the two positions at time 0 and time 6, and in this case that was 36. Now that incredible workaround of avoiding all those infinite sums, that's the fundamental theorem of calculus. You can get infinite area under the curve by just taking the antiderivative, and this thing is hinky, and evaluate. Now that's called a definite integral. This just changed math and all of engineering forever after. Now it doesn't have to be velocity. It could be really any function. So the true fundamental theorem of calculus looks something like this. If you want the area between a curve f of x and the x-axis on an interval, then that sum, that infinite sum, is what's called a definite integral. Definite integrals have bounds, a to b, telling you I want the exact numerical area under a curve of a function. And the way you evaluate a definite integral is you first antidifferentiate and subtract. Now in this case, as far as the function goes, capital F is often used to refer to the antiderivative of any function. I don't want to use velocity every time because it's not always a velocity question. So when you get area under a curve, you antidifferentiate. That's what capital F stands for, the antiderivative, and subtract. And boom, you just made the problem and your life a whole lot easier. This is an alternate form. The area under f prime is the antiderivative, which would be f. I don't want to talk about that too much for a second. Let's look at a problem. Okay? Is this the right place in your notes? Okay. Now, besides the test on Thursday, you will rarely have to do infinite rectangles anymore. Now, you're going to use the fundamental theorem, and your life will be a lot easier. So when I go to evaluate a definite integral, again, it's two steps. First, take the antiderivative, then subtract the two results. So you start, in terms of writing this, you start with the antiderivative. What is the antiderivative? 1/3 x cubed minus 2x. You then draw this evaluation bar saying, hey, that's my antiderivative, so you can check me there. And I'm about to evaluate it, not at just 1x, but at 2, and subtract. So after you antidifferentiate, you have this bar saying these are the values I will put in a minute, but you first need to check my antiderivative. You always must show the antiderivative before putting numbers in. I don't care how great you are. Once you get your doctorate in mathematics, I still don't care. You still show the antiderivative first, then you show the values going in. That's just how it's done. Okay, 1/3 x cubed minus 2x. So when I have this evaluation bar, you evaluate at the upper limit first, the right endpoint. Okay, so when I put 4 in, I get 4 cubed over 3 minus 2 times 4. And then when I put 2 in, I get 2 cubed over 3 minus 2 times 2. You see where I'm coming from? Okay? In terms of evaluating this, now, if you're wise, you'll listen to the hints of an old guy, because we didn't have graphic calculators, and so as far as evaluating definite integrals, I've done thousands more than any BC student ever has, because they are calculator dependent. Okay, so please listen to me carefully in terms of doing this quickly. These should rarely be simplified. Instead, they have built-in common denominators. You should combine those because they both come from the divided by 3. All right, so don't worry about simplifying this or that individually, even if they reduce. Don't reduce them because these will combine nicely. So it is 64 thirds minus 8 thirds. 56 thirds. You see what I'm saying? I don't really care what this in here works out to be because then I'm going to have to combine it with these. Instead, I'm going to look at those. 64 thirds minus 8 thirds is 56 thirds. And I'm going to look at this. This is negative 8 plus 4. Negative 8 plus 4 is negative 4. And if I get a common denominator, it's 56 thirds. Oops, I kind of blew off the plus C. You're probably wondering what's going on there. Sorry. 44 thirds. You follow me? Are you with me? Okay, sorry. So I forgot in my notes I had that plus C. So, sorry, going back. Wouldn't you agree that we typically, when we anti-differentiate, we have a plus C here, right? Now, sorry, it's not my habit to ever write that plus C because you'll see why. When you get a plus C here, it would be here, but also here. And so every time you do a definite interval, every time the C will always go away, okay? So you rarely write the plus C, not rarely, never write the plus C in a definite integral because it always subtracts away every time. So that's why I failed to put that, so it's just my habit not to put it in a definite integral. But if you're thinking, where did the C go? It always subtracts away in these cases. You with me? Are you with me? Cool. Now, if you were to talk about what you just found here, it would be x squared minus 2's area from 2 to 4. Where would that? So that's probably about the net thing we just found is about that area. All right? Now, try on your own, please. Evaluating those two definite integrals. When I say evaluate, you find the antiderivative and then subtract upper at the uppermost slope. Ready? What's the antiderivative? Okay, so that's the antiderivative. Now you put pi in, negative cosine of pi. Put 0 in, negative cosine of 0. And then you subtract. What's cosine of pi? Negative 1. The opposite of that, though, is 1 minus negative. And what's cosine of 0? 1. And minus negative is positive, so the area under the curve is 2. That's a little shocking to me that the area under a sine curve with degrees or radians going all is just a clean 2, but it is true. The area is 2. All right. Would you, if you haven't already finished the other one, try the other one, please, and we'll go over that. All right. What's the antiderivative? Perfect. When you evaluate it at 2, what do you get? And when you evaluate it at 0, what do you get? 1. So e squared plus 4 minus 1 is? E squared plus 3. That's it. Okay, that is the perfect area under the curve. And you could never have done that with infinite rectangles because we don't have formulas for area under e to the x or area under sine of x. There's no formula for the sum of a bunch of those. So this is actually the only way to do those. Okay. What the heck? This thing is freaking nuts today. Everything is bothering me. What in the world? Okay. Let's see. Shall I walk through these or should we go? Yeah, it's important. All right. So let's do an uglier one. So first of all, what's the antiderivative of x squared? Steph? 1/3 x cubed. Lexi, what's the antiderivative of 2x? Beautiful. Anjali, what's the antiderivative of -4? Okay, wonderful. Now let's talk making our life easy. When I go to evaluate, when I put in 3, I'll get 27/3, do not reduce, plus 9 minus 12, minus, do you see where I'm coming from? Okay, 1/3 plus 1 minus 4. Really, if I look at all these 6 terms, there's really only 2 types of terms. 27/3 minus 1/3 is 26/3. In other words, I don't feel the temptation to simplify inside the first bracket and then the second bracket. Instead, I'm going to think if I were to distribute and combine like terms, I would get 26/3. Now the whole numbers, I could do those pretty well. Wouldn't you agree that this would be -3 minus -3? What's -3 minus -3? 0. So my answer is 26/3. Okay. Would you? We actually talked about. We talked about negative areas a little. So this should be reinforcement of that, but let's go with this. If I were to sketch this, isn't this exactly like the velocity we already did? Okay. Except only from 0 to 2. Wouldn't you agree this is an upward opening parabola, but the part they ask about is from 0 to 2? And so because of that, if I were to evaluate this, I feel like I should get a negative. In this case, before I integrate, I would probably distribute, then integrate. So what is the antiderivative of x squared, Harrison? 1/3 x. And the antiderivative of 2x, Jake? X squared from 0 to 2. When I evaluated at 2, I would get 8/3 minus 4. And when I evaluate it at 0, I would get 0. So 8/3 minus 4 is negative 4/3. Now this is negative because the y values are negative, yeah? So last thing of the notes here. When can you expect a negative? There are 2 times you can get a negative. When might I get a negative, and is it okay? You might get a negative if the y values are negative, which would mean the curve is below the axis, x-axis, yeah? You also could get a negative if delta x is negative. For example, if I said something like, all right, the curve is normal log y equals x, which is above the axis, yeah? But if I went from 2 to 0, going from 2 to 0 is going backwards, horizontally. That's from x equals 2 to x equals 0. So delta x is negative. If I were to evaluate that integral, you would actually get a negative answer, not because the curve is negative, but because you're going backwards. That's a definite integral we'll talk about, but to answer the question at the end of the day, is it okay? Yes, negatives are okay for definite integrals. Cool. Now, here's the thing. You have 46 and 46 extra practice. And if I am under the impression that 46 extra practice was not going great. Okay. Well then, should we get 46 questions, a couple 46 questions, and knock that out, and then just hit 46 extra practice tomorrow?
Yes.
All right, let's do that first. So, 46 questions. 3, 3, 3, 2, 1. Not 1. Sorry, I was just assuming that was the pattern, but you didn't say 1. 3 and 2. Are those replacements or book? Okay, cool. Okay, there we go. 46, 3. All right. First of all, get your picture lined up. Do you agree that he is walking away from the lamppost, if I recall? All right, so in terms of the light, what the heck happened? What the heck? All right, so in terms of the light, it looks like that, yeah? Yeah. All right, it is important that to do this well, you need to understand in the picture what's constant, what's varying. Here's the 5-foot man. Is it constant or varying? If it's constant, put the number down and leave it there. Do not make it a variable. What about the height of the lamppost, 35? Is that constant or varying? Constant. It does not vary. Call it 35. What about the distance of the man from the post? Is that constant or varying? Varying. What did you call it? And what about the length of the shadow? Is it constant or varying? Varying. It is varying. I'm going to call it H for shadow. My S's tend to look too much like 5, so I'm going to call it H for shadow. You follow? All right. After you get the variable, now it says, be careful here, it says, how fast is the length of the shadow changing when he's 12 feet from the lamppost? So it's very tempting to say, oh, so this is 12. That goes to, is he always 12 from the lamppost? No, if he's walking away, he's not always 12. So please don't put a 12 here. It's not always 12. Don't say it's constant. It's not. The 12 goes in later. What do they give you? If he walks away from the lamppost, what's changing with time? Right, so dx dt is x increasing or decreasing? Increasing. And what was the, how fast was he? 3 feet per second, yeah? They want, what do they want and when? STT, the shadow, when x is 12. That x equals 12 is the instant. It's not always 12. It's just when the shadow is 12, then find the HTT. So the equation, you have, when you see a triangle, you should think, all right, is it Pythagorean theorem, similar triangles, or trig? What in this case is it? It's similar triangles. So by similar triangles, I'm talking 35 is to 5 in the heights as x plus h is to h, eh? By similar triangles, then what's the cross product? 35 is to, or not the cross product, the ratio. 35 is to 5 as? Okay. There was a problem like this in the homework before. You'd done related rates trying to prepare you for this and make your life easier. A smart problem solver makes their life easy. And the easy way here is to definitely not take the derivative on that yet. What should you do first? Yeah, if you cross multiply or reduce first and cross multiply, 7h equals x plus h, or 6h equals x. That is a heck of a lot easier to take a derivative on than that big ratio. Now let's take the derivative with respect to time. What's the derivative with respect to time on the left? 6 dh dt, and the right? The x dt. Now we know that dh dt then is 3 over 6, or 1/2 foot per second. And the shadow is growing at 1/2 of a foot every second that passes at that point. Okay? 2. At the very least, maybe getting you started on 2. 2. The ladder. Here's a ladder leaning against a wall. That ladder being 10 feet, does it change or is it always 10 feet? Always 10 feet. It's sliding down the wall. So will the vertical distance change? Let's call it y. Will the horizontal distance change? Let's call it x. Cool. You're given that the base is pulling away from the wall at a rate of 1 meter per second. So what are you given? The x dt is 1. They want how fast the top of the ladder is sliding down. So what do they want? When something happens. When what time? When the base is 4, so x is 4. What's the equation we should use? Yeah, by Pythagorean theorem, 10 squared equals x squared plus y squared. Now you can differentiate with respect to time. You should be good. Okay, make sure I get 46 today. We'll go over 46 exercises in class tomorrow. Tomorrow's lesson's not as long. Have a great day. Thank you. Thank you.